Very good morning to my dear students. I, Harita Malani, delivering online lecture on subject fiber optic communication, and the topic to be discussed in continuation with previous lecture on coupled mode analysis of directional coupler. I am working in Electronics and Communication Department of MLB Textile and Engineering College. And today we will discuss, in continuation with my previous lecture, coupled mode analysis of directional coupler. So we'll start. We have discussed basic couplers. Why couplers are designed? These are the basic element of WDM devices. Now we will discuss some wavelength selective devices. The couplers can be designed by using wavelength selective devices. This perform their operation on the incoming optical signal as a function of the wavelength. That means these devices are dependent on wavelength. We will select the particular wavelength. That wavelength optical signal will be transmitted, combined, or any kind of operation we can perform. The examples of wavelength selective devices are wavelength add drop multiplexers, wavelength selective optical combiners, wavelength selective switches and routers. So all these are the applications of couplers. So basic star coupler we have discussed earlier. So some important parameters in short we will discuss. So it have n inputs and m output ports, and the power coupled is 1 by n and average of all the power of the output. So this is my input, this is my output. Can be wavelength selective or non-selective. Coupler can be designed depending on the wavelength or independent of wavelength. Up to n is equal to m is equal to 64. This is a short, quick discussion which we have studied earlier. So this is a basic network of star coupler. How many inputs? 8 inputs and 8 outputs we have used. So n number of input, m number of output. N cross m star coupler. If n is equal to m, so n cross n star coupler we can say. It could be 7 cross 7, 8 cross 8, 1 cross 19, anything it could be. This 1 cross 19 means it is having only one input and 19 outputs. Splitting loss. Whenever this fiber coupler power is splitted, that loss is known as splitting loss. We are considering n cross n means n is equal to m. So splitting loss is given by minus 10 log 10 1 by n, or 10 log 10 minus n. Fiber star excess loss is given by 10 log p input upon summation p output to I. Total loss is splitting loss plus excess loss. So this is the basic of star coupler. So a star coupler is useful when multiple signals need to be combined and broadcast to many outputs. It is an n cross n star coupler with n inputs and n outputs. So this is mentioned in the theory. Now this is another coupler which we have discussed earlier. But some important parameters we are discussing over here. Fused biconical coupler, or it is known as directional coupler. So here input power through fiber 1, that is denoted by P0. Output powers throughout power are denoted by P1 and P2. For fiber 1, P1, fiber 2, it is P2. And the reflected back power is denoted by P3 and P4. These are the powers which are not utilized. They are P3 and P4, and they generate the crosstalk within the optical fiber. So here we have defined three regions. L, tapered region from this end to this end, the tapering of optical fiber where they are coupled. Coupling region is denoted by width W, and again the tapered region is L. So overall length we can say 2L plus W. Is it clear? P3, P4 should be very low, otherwise your signal will degrade. So coupling splitting ratio is P2 upon P1 plus P2. This we have discussed earlier. If P1 is equal to P2, it is called 3 dB coupler. This is the basic of directional coupler. We have all studied. This is the symbol we can say for directional coupler. Now just discussing its fabrication and how it is denoted. So fabricated, it is fabricated by twisting together, melting and pulling together two single mode fibers. They get fused together over length W, tapered section of length L. Total draw length is 2L plus W. This we have seen. significant decrease in normalized frequency number in the coupling region. Energy in the core leak out and gradually couples into the second fiber. See, coupling losses increases because in the coupling region, the fibers are coupled and the mode can be coupled from one fiber to other fiber. Next, multiplexers and demultiplexers. See, these topics are very much interlinked. This can be used in our next unit also, WDM designing. So, basics we are covering here, multiplexers and demultiplexers. In order to implement a WDM system, a multiplexer is required at the transmitting end to combine optical signals from several sources into a single fiber, and a demultiplexer is needed. It is the opposite of multiplexer. It is needed at the receiving end to separate the signals into appropriate channels. Any wavelength division multiplexer can also be used as a multiplexer by simply exchanging the input and output directions. So an optical multiplexer receives many wavelengths from many fibers. We all know what is multiplexers. Many wavelengths at the input is converted into a single output. An optical demultiplexer receives a beam from a fiber and separate it into its frequency components, which are directed to separate fibers. So here the methods used are prism and diffracting gratings. This we will discuss in next slide. Okay, what do we mean by this? These are the two diagrams showing you multiplexers and demultiplexers. In both of these devices, a polychromatic parallel beam impinging on the surface is separated into frequency components, leaving the device at different angles. See, these are my fiber, this is my prism. The light is reflected over here and at different angles it is reflected. So we will get different wavelengths. Over here. So this is my multiplexer. Based on different refracting prism or diffracting grating, diffraction of different wavelengths. So we can design multiplexers and demultiplexers. Now what do you mean by add drop multiplexer? Multiplexer is a device which will combine many signals into one. So here add and drop. If I am having n number of signals, I want to add one more signal to that. So then it is known as add multiplexer. And in n number of inputs, I want to drop one input. Then it is a drop multiplexer. So we are having this facility in the WDM system. We can add or we can drop any of the signal. So this is my add drop multiplexer. I will just dictate once. Optical multiplexers and demultiplexers are component designed for WDM system. Multiplexer combines several output signals at different wavelengths into a single fiber. Demultiplexer separates a multiplicity of wavelengths in a fiber and directs them to many fibers. The optical add-drop multiplexer selectively removes a wavelength from the multiplex, then adds the same wavelength but with different data. So these are the diagrams of multiplexers and demultiplexer. So this is the diagram first. Second, only one wavelength, split it into two wavelengths. At the output I am getting one. Here we are adding both the wavelengths. Here lambda 1, lambda 2, lambda 3, but I am just sending lambda 1 and I am dropping this wavelength lambda 1. So this is drop, 3 wavelengths coming, I am dropping one wavelength input signal. Here I am adding one more signal, lambda 4, and the output, here I have received two signals are transmitted. I have added one more, so I will receive 3 output signals. Clear? So this is my multiplexer and this is my demultiplexer. Demultiplexing, multiplexing. Drop channels, added channel. So this is the basic fundamental of add drop multiplexer. I think you will understand this concept very easily. And please students, start studying. Prepare a copy. You already have a copy. So right now important topics, draw few diagrams. So that will become very easy for you to understand. Thank you very much. And if you have any doubt, so you can message me, you can call me.